Okay, so now looking at the table of all of the things I just talked about, there's the true class, positive and negative. So the people that have the disease are positive, and the people that don't have the disease are negative. And then we have the predictive class, which is the test. So people that test positive or people that test negative. In the upper left corner, we have the true positive. So those are people that have the disease that test positive. Then we have beneath that, we have the false negatives. So people that do have the disease but that are told that they don't have the disease. The combination of those two are the sensitivity, which is the number of true positives over the number of people that have the disease. So the true positives and the false negatives, everybody that has the disease, whether they're positive or negative on the test. The sensitivity, as I said, is how good we are at determining the people that have the disease. Then in the left column, we have the specificity, the negative true class, which is everybody that doesn't have the disease. At the top, we have the false positive, so the people that were told they have the disease when they don't. And then we have the true negatives beneath that, which are the people that don't have the disease and were told that they don't have the disease. They got a negative on the test. The measure of that is the specificity, which is the true negatives, the people that don't have the disease and test negative over everybody that does not have the disease. And that, again, is just a measure of how good we are at detecting those that don't have the disease. The accuracy is a weighted measure of those two, so it has the true positives and the true negatives, the two classes of people or groups of people that we identified correctly, the people that we correctly got the right test with the right class diagnosis, and then that's over everybody. So it's a proportion of cases where we were accurate. And then another measure of this is the positive and negative predictive value. The positive predictive value is the number of within the people that we've said that have the disease, how many of them actually have the disease. So how good are we at predicting the disease through this test. And then, of course, there's the opposite of that, which is the negative predictive value, and it means within all of the people that we said we didn't have a disease, how many of those can we expect to not have the disease? So it's a really important public health measure because it's based on, more so based on prevalence of the disease, and which can influence the accuracy in which or the validity in which we can determine a test. So, for example, in the season of influenza, there's sort of a beginning that's a lower level of prevalence. A few people have the flu in, say, August and maybe even September, and then that number starts to rise, and there's a high prevalence in the winter, and then it again falls. So, the beginning of the beginning of the season for influenza, there's not a lot of people that have the disease. So most people are falling into the negative true class, the right half of that contingency table. So that, when you look at the equation for positive predictive value, we don't have a lot of true positives because we don't have a lot of positives in general. We don't have a lot of people that have the disease, whether they're diagnosed with it or not. So the numerator, the top part of that fraction, is going to be relatively small compared to the bottom, which is going to be made up a lot of false positives. So our positive predictive value is going to be low in the beginning of a influenza season. When there's a low prevalence, it's going to be low positive predictive value. Whereas if you look at the negative predictive value, if we have a lot more people in that negative side, we have a lot more true negatives. And thus we have a large numerator for the negative predictive value, a large true negative, and a relatively smaller denominator. So we're going to have a smaller negative predictive value. We're going to be better at I'm sorry, we're going to have a larger negative predictive value. So we're going to be better at predicting, seeing that people don't have the disease, which makes sense when you think about it because there are just a lot more people that don't have the disease. So by proportion, we're going to be better at picking them up. Whereas the positive predictive value is going to be low because there just aren't a lot of people that have the disease. Or it's going to be hard to find those positive values. Then when influenza becomes more prevalent, most people move to that left-hand side, so the positive column, and then they have a lot more true positives and false negatives. Just in general, as the prevalence rises, those two groups are going to get bigger, and that's going to increase our positive predictive value because our numerator is going to get big, and then it's going to decrease our negative predictive value because our denominator is going to get bigger as we get more false negatives. So when the prevalence is high, we're better at predicting that positive predicting value. If you want to just fill in some numbers to get an idea, I want you to be able to, if I give you some part of this table, you can fill in the rest of it. So if there's 1,000 people and 100 of them have the disease, so 100 of them are going to be on the positive side of the true class, then that leaves 1,000 minus 100, or 900 in that negative side. Excuse me. If there's 80 people that have the disease that test positive for it, so 80 true positives, then that will leave 100 minus 80, or 20 in the false negative column. And our sensitivity will be our true positives, 80, over everybody who has the disease, 100, or 0.8, 80%. And then our positivity, if we have 100 of the 900 people that don't have the disease, 100 of them test positive for the disease, and 800 are true negatives. They don't have the disease and they don't test positive for the disease. So then our specificity is 800 over 900, or 0.89. So that's just kind of a little example, and I will get into some more examples in a second for the rest of the measures. But that's kind of the breakdown about different measures of accuracy and validity. As I said earlier, the cutoff between, in a continuous test, some outputs for a test are continuous, such as, in this case, we have diabetes, and we're screening it looking at the blood sugar level. And there's no particularly distinctive cutoff between diabetics and non-diabetics. So in this table, or in this picture, we have diabetics that are purple circles and then non-diabetics that are clear. If we pick a relatively low cutoff, we're very good at identifying the people with diabetes. So if you look at our table on the right, there's 17 diabetics and 20 total people. So we have a very high sensitivity based on a low cutoff. Whereas in the right-hand side, in the non-diabetics, we have identified a lot of non-diabetics as diabetics. So we have a lot of false negatives, false positives. And 14 over 20 or 30 is a very low specificity. So in this low cutoff, we're good at identifying the cases of diabetes, but we're not good at identifying people that don't have the disease. If you look at this next chart, this is the same idea but with a high cutoff. So if you look at our table, we, in this case, are very good at identifying those that do not have the disease. So with a high cutoff, we're saying we have a very high specificity of 90%. 18 of our cases of non-diabetics were negative on the test, whereas our sensitivity is extremely low because we have 15 of our diabetics were diagnosed without diabetes. The decision to make that cutoff is just kind of a value judgment based on the specificity and sensitivity and the importance of each of those. If it's a diagnostic test, so if it's confirmatory, it's very expensive, very invasive, you want to minimize the amount of people that you put through that. So you want to minimize those false negatives, and you want to have a high cutoff threshold. Whereas if the penalty for missing a case is high, maybe the test is very cheap and it's pretty easy to administer and easy to take, then you want to maximize those true positives, and you want to have a cutoff that has high sensitivity. So it's really just a balance between the false positives and the false negatives. If the severity of the disease is high and the cost and difficulty of administering the test is low, then you want to have a high sensitivity. So in this case, we would have a low blood sugar cutoff. But if the penalty, or if the test is very expensive and it's hard to put people through, and it's a confirmatory test, we don't want to tell people they have a particularly severe disease when they don't. We don't want to treat people for a disease they don't have. If that outweighs the chance of missing the disease, then we want to have a high specificity. So in this case, we'd have a high blood sugar level as our cutoff. The multiple, as I said earlier, there's a way to do multiple tests. So when you're working with two tests, there's two ways to do it. One is a sequential, which is first test is administered. Generally, those are easy and cheap ways of administering a test. And then all of the positive for that first test are then taken and given a second test. Or there's a simultaneous test, which is multiple tests at the same time. When you're judging the accuracy of two tests, you have to judge them together, and then we come into probability. So the net sensitivity is the probability of either, in the case of sequential testing, it's the probability of testing positive for both tests, because you won't be included in the second test if you're not a positive in the first test. And if we look at our Venn diagrams, we have all of the yellow sort of cream color is people with disease. So you're going to have some people that test positive for test 1 only, and then some people that test positive for test 2 only, and some people that test positive for both. When you have sequential testing, like I was saying, you have people that need to test positive for both. And because these are independent tests, we can remember from our biostats days, probability of A and B is equal to the probability of A times probability of B. And then in the case of testing, in the case of sensitivity, the probability of someone with the disease, so the probability of someone testing positive for both tests is the probability of someone with the disease testing positive in the first test, which is the sensitivity of test 1, that probability that we're identifying people with the disease, times the probability of the same person testing positive in the second test, which is the sensitivity of the second test. In the case of simultaneous testing, where we're giving two tests and the person could test positive for either or, the combined probability is the or function, and it's a probability of testing positive to either of the tests, which is the probability of testing positive for the first test, the sensitivity of the first test, plus the probability of testing positive in the second test, the sensitivity of the second test, minus that overlap. So minus the number of people that tested positive for both, which is the sensitivity of 1 times the sensitivity of 2. I'm going to